I'm Ryan Kooiman, Director of Training here at Standard. I want to welcome you to this month's Power Hour. Today we're talking about fuel pump control modules, and more specifically how to diagnose it. Now, a lot of technicians might not even be aware that they actually exist. Others might know that they're there, but they don't know what they do. So we've got a couple tips here for you. I'm going to share some insight that we've learned through many years of experience in repair here, and also stuff we understand as a manufacturer. So let's get started. All right, well, as mentioned, today's topic is fuel pump control module diagnosis. So let's kind of cover back to some of the basics of fuel pumps. So many of us grew up in the day diagnosing and replacing fuel pumps. Personally, I probably paid for my first mortgage by doing GM fuel pumps in the shop. Those Chevy trucks in the late 90s were notorious for those. So here we've got a brush style pump in the tank, obviously. It's going to be controlled by a relay. So either B plus or ground controlled here. It's going to control the pull-in circuit. And we've got B plus going to it, making contact. And then we're going to power up the pump. Definitely a supplied ground here. And so that's one thing I always encourage technicians. Always focus on the power side, right? But what about the ground side? Got a great story for another time about a truck that had 13 fuel pumps installed because it had a faulty ground. So never overlook the ground there. But on this brush style pump, it's going to be commanded on or off. That's it. No variations. It's just pumping. So as we talk about the current pattern of this and look at the waveform pattern of it, and a lot of the trucks here, we're going to see between 8 and 10 amps of current. Vehicles or smaller displacement engines might be a little bit lower. But for the most part, we're looking for the commutator bars passing by here. There's no dropouts, et cetera, right, that are going to result in that intermittent start or no start. And so right here, it looks really pretty good. And so many technicians have become familiar with this over the year here. And so when it comes time to return the fuel, remember this thing's just on. And so it's blasting as much fuel as it can, volume and pressure wise, through the entire system there. So it's going to send it up to the rails. We've got the injectors here on the rail. But on these early styles, then we had a return line here. And so this return line would return any unused fuel back to the tank. Now, there's a couple problems with this plan. And again, I'm guessing many of you, the experience of same color hair as mine, have been down that path before. So this is going to be a vacuum regulated or a vacuum controlled regulator. Well, what happens when the diaphragm in there bursts? Well, and we've certainly seen that with the onslaught of E85 and increased ethanol percentage in many fuels. And so the diaphragm ruptures, and then it goes into the vacuum line. We end up flooding out the engine, maybe causing a no start or maybe even some engine damage there if that diaphragm ruptures. And so that's one problem. The second problem, and the one that manufacturers really work to address with modern systems, are this return fuel. Now, as fuels come up to the top of the engine, heat rises, right? And so we've got a lot of heat captured in this fuel rail here. And so that return fuel now is going to take heat with it back to the fuel tank. When that warm fuel is deposited back in that tank full of probably cool fuel, that's where we get evaporative emissions. And so it turns into a vapor inside the fuel tank. And so, again, modern evap systems are going to filter that out. Hopefully clean airs come back into the atmosphere, but that's something to take into consideration. And that's what manufacturers, engineers have done over the years. So one of their earlier attempts at returnless systems, now this is off a 2001 Saturn. Again, we're going way back in the archives here. I got a couple people in the studio that probably weren't even alive back in those days. And so these earlier systems, again, the regulator was actually in the filter. So the pump was full bore, commanding on, and then it's giving just what's required to go up to the rail. The rest of it's returned out of that filter back to the tank. So this got rid of that regulator up on the rail. So we don't really worry about the ruptured regulator anymore. But also, it's not getting to the point where the heat is captured with that fuel. So we're returning cooler fuel. Probably not the exact same temperature that was in the tank, but it's definitely cooler fuel. So it made significant improvements at that point, but not perfect, nor is any system yet for that matter. So then mid 2000s, we saw more manufacturers going to this type of design with a pulse width modulated fuel pump. And so this is still a DC motor here. And instead of having that relay, simply slamming that pump on or turning it off, now it's going to be pulse width modulated, duty cycle controlled here to modulate this pump and spin it just enough to meet the demand of what the engine is requiring there. And so we've seen that in a ton of other automotive applications, right? Just yesterday I was doing a session with a group talking about AC compressors. So we've got variable displacement compressors. We've got torque converter lockup solenoids now that aren't fully applied or unapplied, right? It's a much softer variable application. And so that's really what the OE design manufacturers or engineers were going for in this type of scenario. So we've got our fuel pump control module communicating with the engine control module or powertrain control module. It's going to be separately powered and grounded here. And then it's going to control the power side circuit to modulate this pump and produce the amount of fuel pressure and, most importantly, the volume required to sustain complete combustion. So now as we look at the current, remember that earlier example I gave you about 8 to 10 amps? Here's the example of a Chevy truck at idle. And we can see it's about 3 amps of current here. So significantly less amount of work being done here, but significantly less fuel being fed to the engine. So while this thing's at idle, certainly does not require the amount of fuel as it does under heavy acceleration. So that's the thing is we look over to the right-hand side, we've got a separate capture here, and we can see under acceleration, the current ramp is increasing, right? Because there's higher demand. And so now the engine understands we need more fuel. Let's ramp that pump up and supply more fuel to it. So again, it's following the demand or the request of the engine. Then with these, we've got the electronic returnless fuel system. So once more, if we're only giving the engine what it needs, we don't have to worry about returning fuel back there. So one less hose, right? We don't need another line going back to it. One less regulator, a lot less evaporative emissions there. And so this is where a lot of manufacturers, again, kind of landed with their designs around the mid-2000s. And now some technicians are going, yeah, I've seen that, but how does it know? Well, in a second, I'm going to talk about a sensor added to the line here, but most of the ones we're going to be working on today are out of the kind of the 2000s to 2010s model years there. There's no sensor. So what happens? Well, manufacturers have done a great job mapping out the fuel control based on engine load, engine RPM, and throttle position. So the driver's requests, how far or how fast do you want to go, how much torque should the engine produce, what's the actual engine RPM, and then using mass airflow or speed density system, what is the engine load? Now the PCM has a pre-calculated amount and says, okay, we should be spinning the pump at this particular speed. So it's going to send a control signal, or it's going to communicate with a fuel pump control module, which is going to command the pump RPM to increase or decrease. Now, obviously, the fuel system, obviously, with a closed loop type feedback system, we're going to have air fuel sensors or oxygen sensors, which are going to report back to the PCM, say, you know what, it's too rich, it's too lean. And so that will also come into consideration when it's trimming the fuel pump speed. But I just gave you the sneak peek here. We see this on a lot of today's newer vehicles where there is actually a sensor. We might see a sensor on the low pressure side on some manufacturers. Others, we're going to see it on the high pressure side. And so depending on which manufacturer you're working on, it's always important to get a good understanding of what's there, or look on the scan tool, and do we have data PIDs for the low pressure or the high pressure side there. It's going to make a difference. Now, move into the last 5 or 6 years, we've seen different manufacturers moving into 3-phase or brushless DC motors. And so this is significantly much better control. I don't want to say infinite control, but significantly improved control and longevity. If I had to go back in the shop today and make a living off replacing fuel pumps, I would probably starve. And enough on the fat jokes. I can stand to lose a little bit here, but we're not replacing fuel pumps in the same manner as we did in the 90s with the brush style pumps, again, because they were fully commanded on. Now, there may have been some manufacturing defects, design defects, etc. But remember, those things were just full force all the way on. Today's brushless DC motors, they're only going to work as hard as they have to. And so we're seeing much increased service life out of those. And so if you really want to look at the current here, now we have to keep in mind we have 3 different phases here. So we have to be a little more strategic when we current ramp our fuel pump. And so in many cases, we're going to go to the supply feed to that actual module with our current probe, and then we're going to see something similar to this. And so in the drive cycle, you can see the variation of the increases, decreases. What we've done here is applied a filter. So you're seeing the same thing right below here. This is the same thing, but it's just kind of filtered out. So it's a little bit cleaner to see. But you'll see under even acceleration, this thing's only pulling 3 amps. And that's dropping down to about 2.5 amps here. And so I want to help illustrate once again, by less current, that means less work is being done there. And so this is a much more efficient design system. And so ultimately, this is where we end up today with a lot of the brushless DC motors here. ECM talking over the data link connector or via the CAN network to the fuel pump control module and communicating with the brushless fuel pump. And then we've got the feedback here via one or multiple, in some cases, pressure sensors. So here's a tech tip I want to share with you. I've got a couple of them that have come out of one of our classes here. It's a full 1 evening class on fuel pump and fuel injection strategies. But this is taken from a 2010 Chevy Tahoe. So it's already 16 years old vehicle, or 17. And I want to make you aware that on some of these vehicles, the trailer brake control module is part of the fuel pump control module. So I've actually got one here, replaced it as of late, and doing some testing on one of these things. These are located underneath the vehicle, mounted on the frame. So if you're like myself, you live in the northern states, there's a lot of road grime, corrosion, salt, slush, etc. on these things. So you may have already replaced some of these things. But keep in mind, there's options with trailer brake control module and without trailer brake control. And so the modules might look identical to each other, but they're going to have different functionality. So if you're going to work on one of these, you need to look at the RPO codes, or a good, quick, easy way on a lot of these is to look on the dash. You know, GM's got that little slide piece there. So make sure when you're ordering one of these for the mid-2000s or 2010s GM trucks, make sure if you have a trailer brake control module or not, because it's most likely going to be incorporated into this fuel pump control module. Now, here's one I actually ran across on TikTok. A General Motors dealership technician I follow was going through a diagnosis, and the evap vent is actually controlled by the fuel pump control module on a 2020 Chevy truck. And so how many technicians, if they're running across a shorted vent solenoid or something along that lines, they're automatically thinking it's controlled by the PCM? No, it's actually controlled by the fuel pump control module. So as different manufacturers get the PCM circuits overloaded, information overload, they can only process so much at a given time. And so they're actually going to incorporate it into different modules. Somebody probably said, hey, this module's back there, it controls fuel pump stuff. And so that's where, if we look at the wire schematic here, we can see the fuel pressure sensor is reporting back to it. We've got the fuel pump assembly here. So we've got the 3 different phases being controlled here, fuel level assembly. And so that's all inputs to it. And so if I look at just the fuel pump control module schematic, this is what I see. But this is one of those tips we have to sometimes dig a little bit further. As I'm looking at the evap schematics, we can also see that this is controlled by the fuel pump control module. So keep that in mind. More than just fuel pump control is happening with some of these modules. Here's my final tip to share with you. Again, I'm very involved with our warranty process. When we look at some stuff that might come back, always scouring different tech forums. And this is something that quite often is overlooked. And it's confusing because on this particular truck, a Chevy 2010 Chevy Tahoe, as we look this up, it says if the fuel pump control module is replaced, it must be programmed, refer to service programming system. So on this 2010, it is. But I also looked it up on a 2012, and that one says if you're replacing it, no programming is required. So the most dangerous scenario is for a technician to install one in a 2012. They don't require any programming, right? Next rolls in a 2010, and they don't even consider, they don't talk to the service advisor about it. They might not even have the tools available to do the programming. So that's where anytime we're making a diagnosis and going to replace any type of control module, I'm always going to recommend that you look in service information to determine, do I need to program this? And then it comes, can I do this? And how much are we going to charge the customer for this? So let's be aware of this before we even make that initial quote to the customer. So let's look at a couple recordings here from a couple other vehicles. So if you're not familiar with looking at scan data for these fuel pump control modules, a couple things I want you to be aware of. So this is off one. I just drove it the other day. Actually got the truck in the studio here. And so we can scan just standalone the fuel pump control module. Now we have ECM data, but we're going to go into the fuel pump control module. And so we can see the desired pressure, obviously quite straight. So that's 43.5. And then we've got the actual. So the actual is 43.5 also. Now you see a little bit of noise in here because it is fluctuating. But if we look at the scaling, it's only going up maybe a PSI or down. So it's really tracking quite true. But if we look at the command signal to that pump, it is varying here. Not significantly. So we're from 37 to 29 on the low side. So it's just variably changing here, that command. But what I want to talk about a little bit here is the fuel pump trim. Now, as technicians, we found fuel trim to be a huge assistance or huge diagnostic aid when talking about drivability concerns. And so we're seeing short-term fuel trims and long-term fuel trims. And so the temptation is now I'm looking at fuel pump data and I see short-term fuel pump trim and long-term fuel pump trim. And now put on my other hat and go, well, this is going to be like fuel trims. It's not. These things look pretty straightforward here, right? The long-term is perfect. See this short-term, it's only changing like 0.1%. And so one thing I want to caution you is to not get too excited by looking at these trim PIDs. Very rarely are you going to see much significant movement on them. And we talked to GM field service engineers, like we don't even pay attention to those. Quite often they're flatlined. And so we want to look at actual or the desired actual and the pump command here. One perfect example of that is this is a 2009 GMC Sierra, which came into a shop with a fuel level concern. So they did what most people are going to do. They're going to replace the fuel pump assembly, right? The level sensor is part of the assembly. So they installed it and the vehicle was fine. The level seemed okay. Well, the truck came back with a check engine light on like 3 days later. And so they scanned it, had some trouble code stored in there. What they came to find out is this pump was actually producing excessive pressure and excessive volume. And so the hope is that the trimming here or this command would pull it back within range. And so that's kind of my point here is sharing there's very minuscule control on some of these earlier GM fuel pump control modules. So while it's a good theory and it can ramp it up and down based on the demand, when it comes to overall adjustments, we're going to see very, very minor changes here. And so this one eventually took another fuel pump to bring that fuel pressure and volume back within the specified range. And so here we see the fixed information, and there's not a whole lot of significant change. Yes, we see some of this, it looks big on the screen, but in all reality, we're talking about 0.1% here. And so it looks big based on the scaling. So kind of my reminder on these GM ones, again, we're going to look at the desired, the actual, and the command. But keep in mind, we're not going to see significant reduction or increase based on any of these trim numbers here. A couple of common DTCs and ones that we saw actually in this particular truck. fuel pump flow performance. So if we've got a check engine light on, that's why the truck came back to the shop, remember? And so first off, we got a P069E, which is fuel pump control module request of the mill. And so quite often we're familiar with like that P0700, which is telling us, hey, the trans control module turned on the check engine light. This particular one is saying, hey, the fuel pump control module turned on the check engine light. And so we scan the fuel pump control module and we find here this 2635 fuel pump flow performance code. In this particular one, technician looked at the diagnostic tree and determined this pump was actually outputting too much fuel pressure. So that's another reason why when we're working on a lot of these vehicles and the parts department or the catalog asks for a specific VIN, you give them the correct VIN because there's a lot of different options. A 5.3 is not always a 5.3, right? Some are going to have different pressures and different readings there, different regulators, etc. So we need to be careful with that. Also, another common code here is the P0191 fuel rail pressure sensor circuit performance. Now it says circuit performance, but this was actually a faulty pump. And again, that circuit reads 0 volts. There's not actually 51 kilopascals in the rail. That's kind of the default number there. And so 0 volts, it wasn't actually a faulty circuit. There just was legit no pressure on the rail because of a faulty pump. So we follow the diagnostic procedure. So let's take a look here at another manufacturer. Now, different manufacturers are using different strategies. And so because of the time constraints, I'm really only covering GM and Ford here today. So let's do a quick overview of some of the Ford electronic returnless systems here. Now, personally, for my days as a technician in the shop, this was my introduction to fuel pump control modules. So think about Fords. Many of them for years and years and years, or really since the inception of the electric pump on Ford vehicles, have used an inertia switch. I've, again, made some pretty good money by customers having a bowling ball rolling on the trunk of their car and hitting the inertia switch so the car gets towed in, and we simply trip the switch, remove the bowling ball, and send them back on their way. Or somebody kicks the front kick panel and trips the inertia switch. So Ford used that inertia switch for many years, but around 2010, they made a change and removed the physical inertia switch and moved it to the restraint control module. So if there's an impact detected, and remember we've got impact sensors all around the vehicle reporting to the SIR module, or the supplemental inflatable restraint module. And so that's going to report, and if there's a collision reported, that's going to cut the fuel pump. Not because they want the car to die, but imagine somebody sitting upside down in a car. We don't want that fuel pump to continue running there. And so in many cases, we don't want that pump to restart again. And so on these particular vehicles, if it's set a trouble flag in the restraint control module, we have to go in and clear the memory from it in order to get the fuel pump driver module to turn the pump back on again. So it's gone from a physical inertia switch to more of a virtual or electronic inertia switch here. So yes, we still got the control relay sending power through that restraint control module, fuel to the driver module, pulse width modulation coming from the ECM to the driver module. It's going to pass that along to the pump here and command that pump speed. So as we look at some of the command signals here, we can see the pulse width modulation. We've got the initial spike when the key was turned to the run position, right? That's kind of that wake up signal, prime the fuel system. Then it's going to shut off. Now we can see as the driver cranks the vehicle, we've got the pulse width modulation making the command here. We can see the current significantly increase, and it kind of settles out throughout the cranking position, and then it shifts down to a lower mode there as needed. Then as we look at some of the scan data here, I just want to call out a couple things. If you're familiar with the Ford scan tool or not, anything with the pound signal here means it's bidirectional control. So we can actually turn this on. So fuel pressure here, or fuel pump command, we can see it's in a percentage. We can actually click on that and ramp that up or down. But so we can see the fuel pump command, we can see the fuel rail pressure in PSI, which is an inferred reading, the actual voltage that's coming from the sensor. We can see the desired, then we can see our long-term fuel trims, engine RPM, short-term. Now, this is not pump trim like what we were looking at on the GM, but this is true fuel trims, fuel trims. One thing I want to call out here, though, is on Fords when they're showing the fuel rail pressure. Now, this particular vehicles, if they got a rail pressure sensor, they're not going to have a Schrader valve in the traditional sense. However, where there's a will, there's a way. And I've seen many times a technician find a way to hook up a mechanical gauge. And I want to warn you, this reading is going to be different than what you're going to see on your mechanical gauge. Why? Because your mechanical gauge will be referenced to atmospheric pressure. The way these are used or set up, it's going to be referenced to manifold absolute pressure. So I'll show you what that means here in just a second. But we're going to kind of look at that in the context of a broken truck. So this is a 2006 Ford 5.4 liter, 82,000 miles on it. And the customer's concern, crank no start, has 2 new fuel pumps. And so we all love these stories, right? Well, I was at a job site and there was a bunch of concrete guys there. They said my truck wouldn't start because it needs a fuel pump. They said they'd do the fuel pump on the side for me. So they installed the fuel pump. It still didn't start. Well, it must have been a defective pump. So they put a second pump in it. Still doesn't start. Now we're actually getting it towed into the shop. So I don't know about you, but I always hate being the second or third person that touched a vehicle. But hopefully the customer has a little bit of money left over to actually spend on the correct diagnosis and repair. So that's where we're going to pop the hood, take a look at this. And this is what I was referring to, the fuel rail pressure sensor here. It's mounted on the rail, but you'll notice that there's a vacuum line going to it here. And so this vacuum line is going to be hooked directly to manifold vacuum. And so it is referencing manifold vacuum. So that's going to change the offset. And so what that's doing, what you're reading here is what we're seeing at the tip of the injector. Remember, on these port style injection systems, the tip of the injector is going to be inserted into the intake manifold, which is going to be quite often under vacuum. And so by monitoring or referencing it off manifold vacuum, what we're reading is the same thing that the injector is actually seeing at the tip of it there. Your gauge, once again, is going to be referenced to atmospheric pressure. So that's where you're going to see the 2 differences there. So hopefully you understand that. So the technician plugs in a scan tool and is going to retrieve some trouble codes here. We got a 1233 fuel pump driver module offline. So before getting out of the truck, let's take a look at some of the data as we try and start the truck here. 50% command, which should be turning that all the way on. We've only got 8 PSI in the rail. So we got a brand new fuel pump, right? So we can look at the wire schematic here. It's got 2 new fuel pumps in it. So do we want to drop the tank yet? Well, let's hold on a second. And so as we look at that, here's our fuel pump, and it's got a shield wire here connected to the ground. And then our 2 wires go to the fuel pump driver module. So kind of the technician's game plan here. We want to make sure that our relay is working fine, make sure that our inertia switch is okay. And so we've got power going to the fuel pump driver module. And then we also want to measure our signals, the command signals from the PCM to this fuel pump driver module. So the technician looks in service information while he's at the wire schematic, says, okay, this particular component is going to be at the rear frame rail cross member, actually above the spare tire. And so those of you in the Rust Belt are probably very familiar with something like this. You probably replaced a lot of these as well. So we don't have to do a whole lot of brain bending or letting the smoke out between our ears here. When we're looking for this fuel pump control module to do the testing of signals here, this thing is aluminum and it's mounted to a steel cross member. And those 2 dissimilar metals don't like each other. And so that's where we see significant increased corrosion. And so this thing was physically split wide open. And so you could see water and different corrosion in there. Here's another view of it after it came off the vehicle. So that's pretty nasty. So before we get too far into it, we have to go ahead and replace this. One thing I learned from a technician, and again, being a tech myself, we're always looking for tips, right? And how can we get this truck in the vehicle? I'm doing this testing actually out in the parking lot. It's hot in the sun, and I want to get it in the vehicle or in the shop, put it up on the hoist. And so what I learned from a technician in class, as we go back here, we can actually take a fuse, like a 15 amp fuse, and connect it from here to here, it fits in perfectly as we look at the connector here. And so it'll fit perfectly to bring power from here into there. So essentially you really bypass that fuel pump driver module to full field the pump. Now we're not going to send the customer on the road that way, but that's going to allow us to drive the vehicle into the shop, get it up on the hoist, and do the actual work here. So we're going to work smarter, not harder, right? So here's the new and improved design fuel pump control module. You'll notice that it comes with new mounting bolts. So these bolts are actually going to go into that frame rail, and you see that you've got the nuts here with some spacers, and what that's going to do is keep that module mounted just about a 1/4 inch off the frame rail there. So it's going to prevent it. As we can see here, this aluminum housing is no longer touching the steel frame rail there. So once we've installed our new fuel pump driver module, turn the key. Well, we're at 20% duty cycle command here, and we're approximately 40 PSI. The truck starts and runs. So did it need a fuel pump? I'm going to say no, but the people that did it are probably going to say, well, that's what took out the module, or the module took out the pumps. And so, technicians are always very creative on covering their tracks for a previous misdiagnosis here. So hopefully you have a little bit better understanding of what it takes to diagnose and replace one of these particular modules on the Ford F-150. And you remember the difference in the fuel rail pressure sensor reading. So kind of as I wrap up this segment here on fuel pump control modules, always look up service information. Look it up. How does that system work? What's known good? What's the theory and operation of that? Do I need to think about these short-term or long-term pump trims on this? I'd love to hear from some of the audience in the future and go, hey, I've experienced this, or comment, as we mount this on YouTube after our live viewing. Love to hear your thoughts on some of that, or some of your experiences on that as well. We need to thoroughly read through the system description here. Reading comprehension skills have never been more important in the automotive aftermarket as they are today. Follow instructions precisely. What does it say to do? Well, do it. Do I need to program it? Do I not need to program it? Take a look at the specific vehicle you're working on. And then we always want to verify the repair. And so the customer brought the vehicle to us with this concern. We're going to do the work. We're going to take their money, and we need to make sure that it's actually, we've taken away the problem from them before we give it back to them. So, as we kind of wrap up here, if you're looking for more information, you can always go to our Standard Brand YouTube channel. That's where you can find some of our previously recorded Power Hour sessions. If you've missed some of these, or you want to review them again, or find more information. We've got a ton of different installation tip videos. We've got installation guidelines. We've got more information about our products, what's in our box. And you're going to learn more about our products, more about diagnosing and repairing these successfully. So if you want even more information, you can definitely go to standardbrand.com, our website, and you can click on training here. You can click on products. You can even look at our e-catalog there to find out more information about the vehicle you're working on. I still do that quite often. You call the parts store and they go, it looks like it's a dealer-only part. Nope. I looked it up on the standard e-catalog. It's available through them. And so sometimes you have to give them the part number or help encourage to get that special order part there. Patrick, I see you've been answering a few questions in the background here on the Q&A, but what are some of your favorites that you want to share with the whole audience?
Mills wants to clarify, in that earlier GM scenario, the module was unable to pull the fuel pressure back to within spec due to the faulty pump, right?
That is absolutely correct. So that's kind of it was disappointing for me. I thought that the command would be able to bring that pump within a range, but it didn't. And so, it required a new fuel pump yet. So you are correct in your understanding there.
We've got Henry here that wants to know if Ford and GM are the only ones that use fuel pump control modules.
Nope. Good question, Henry. And I wish I had the full 4 hours to give you here, but different manufacturers, Honda, or Toyota's, I've got experience with that. Different manufacturers use it for many times. Think of Mercedes has been using brushless motors for a lot longer, obviously through a control module. So we've had enough time to share these two common manufacturers, which I think probably roll most prevalently through our shops.
Lastly, we have Kevin. He's asking, are there any performance flashes that improve performance?
There may be, but I don't want to comment on that. And so fuel, so when somebody talks in the performance world, fuel is one of the easiest things to add for any manufacturer or OE engineer. Now, we live in the OE specified world here, but if you're in the performance world, it's more so about getting airflow in versus trying to reflash your pump control module and get more pressure out of it. So I'm going to kind of reserve some judgment on that, but in most cases, no, you're not going to increase the output of the pump by reflashing or changing some parameters on that particular control module. So good. All right. Well, thanks again for the input and the questions here. And so we look forward to seeing you at the next Power Hour.